Hello all, welcome to the class of Discrete Mathematical Structures 18 CS 36, Module 1, Fundamentals of Logic. I'll be teaching a topic in Fundamentals of Logic. The topic is about converse, inverse, contrapositive and logical implication. Myself, Dr. Madhura, Assistant Professor, Department of Mathematics, Sai Vidya Institute of Technology, Bengaluru. First, we will know about the NAND and the NOR. The compound proposition negation of P and Q read as not P and Q. Negation symbol is read as not. This is read as P and Q. So not P and Q is denoted by P up arrow Q. The up arrow is read as NAND. So P NAND Q. The symbol up arrow, which is a combination of not and, is called as the NAND connective. So now we are discussing about two connectivities. One is NAND, the other one is NOR. So NAND is a combination of not and, which is denoted by this symbol, which is upper arrow. Therefore, P NAND Q is logically equivalent to negation of P and Q, which is logically equivalent to negation P or negation Q using De Morgan's law. The compound proposition negation of P or Q, which is read as not P or Q, is denoted by P down arrow Q. The symbol down arrow, which is a combination of not and or, is called the NOR connective. So NOR is a combination of not and or. That is the reason we have negation. Not stands for negation. P or Q. P or Q. So negation P or Q gives us P nor Q. P nor Q, which is nothing but the symbolically down arrow representing. So therefore, P nor Q can be written as, which is logically equivalent to negation of P or Q, and this logically equivalent to negation P and negation Q. Using De Morgan's law, negation of P or Q becomes negation P and negation Q. Now we will see the truth table for the same. So we have P and Q as the propositions, which takes the values 0, 0, 0, 1, 1, 0, 1, 1. P and Q. P and Q is true only when both P and Q are true. So we have 1 here for P and Q. The rest all values in the P and Q are 0. Only when P and Q are taking the truth value as 1, the resultant for P and Q is also 1. So rest all cases it is 0. Now the negation of P and Q. Negation of P and Q is negation of 0 is 1, negation of 0 is 1, negation of 0 is 1, again negation of 1 is 0. So this is the truth table or the truth values for P NAND Q. NAND means it's a combination of not and. Now similarly we'll write down for P or Q. So P or Q is true when either P or Q is true. So either P or Q should be true to say the truth value of P or Q is true. Only when both P and Q are taking the truth value as 0, P or Q truth value is 0. Now negation of P or Q will be Negation of 0 is 1, negation of 1 is 0, negation of 1 is 0, and again similarly negation of 1 is 0. So this is the truth table for P NOR Q. NOR stands for combination of NOT and OR. So this is how we write down the truth table for NAND and NOR connectives. We note that P NAND Q and P NOR Q are duals of each other. Converse, inverse and contrapositive. Suppose we consider a conditional P implication Q. This is a conditional for us. Then Q conditional P or Q implication P is called the converse of P implication Q. The right arrow is read as either conditional or it can be read as implication also. So Q conditional P is called the converse of P conditional Q. That's how a converse can be written for a conditional. Similarly, inverse. Negation P conditional negation Q gives us the inverse of P conditional Q. Negation P conditional negation Q gives us the inverse of P conditional Q. And lastly, the contrapositive, that is negation Q conditional negation P gives us the contrapositive of P conditional Q. So P implication Q is the given conditional for us. For this, the contrapositive is negation Q implication negation P. The truth table for the same, that is for converse, inverse and contrapositive, are as below. So firstly, remember that converse is given by Q conditional P, inverse is given by negation P conditional negation Q, and contrapositive is negation Q conditional negation P. So we are writing the truth table for the same. P, Q are the propositions for us, which takes the truth values 0, 0, 0, 1, 1, 0 and 1, 1. We take negative negation P and negation Q. We write down the negation of each of the values. Then we will be able to write down P conditional Q. Recall, P implication Q is 0 only when P is true and Q is 0. P conditional Q is taking the truth value 0 only when P is 1 and Q is 0. Rest all cases it is 1. This is from the definition of implication or the conditional. Next we have negation P implication negation Q. So negation P implication negation Q, we'll look into the third and the fourth column. So again when you have 1, 0, the truth value is 0. Rest all cases it is 1 only. Next we take Q conditional P. So first we read the second column, then the first column we are reading. So that gives us Q conditional P. So we have 1, 0 in the second row. 1, 0 in the second row. So only when you have 1, 0 in the implication, the resultant is 0. Rest all cases it is 1. And lastly, negation Q conditional negation P. Negation Q is the fourth column. We read the fourth column first, followed by the third column. So in fourth column 1 and third column 0 is in the third row. So only when it is 1, 0, the truth value is 0. Rest all cases it is 1. So that is how we obtain negation Q conditional negation P. Now, Q conditional P gives us the converse, and then negation P conditional negation Q gives us the inverse. Negation Q conditional negation P gives us the contrapositive. Now, from the truth table, we can conclude that P conditional Q is logically equivalent to negation Q conditional negation P. We observe the truth values of P conditional Q, that is the fifth column, and the eighth column, so negation Q, conditional negation P, they have the same truth values if you observe. So it is 1, 1, 0, 1. Here also it is 1, 1, 0, 1. So since P conditional Q is logically equivalent to negation Q, conditional negation P, we also observe the columns, that is 6 and 7, that is Q conditional P is logically equivalent to negation P, conditional negation Q. Q conditional P, that is 7th column, is equal to 6th column truth values. So these two will help us to say that the conditional and the contrapositive are logically equivalent, because P conditional Q is logically equivalent to negation Q, conditional negation P. P conditional Q is nothing but the conditional. Negation Q, conditional negation P is nothing but a contrapositive. So these two are logically equivalent. That is the first statement here. Then secondly, the inverse and the converse are logically equivalent. So inverse is given by negation P, conditional negation Q, and the converse is given by Q, conditional P. So they are logically equivalent to each other. I just repeat the same thing. P conditional Q gives us the conditional. Negation Q, conditional negation P gives us the contrapositive. We observe they are having the same truth values, so they are logically equivalent to each other. Then we have Q conditional P, which is the converse of the given conditional. So Q conditional P has the same truth value as negation P, conditional negation Q. That is nothing but the inverse of the given conditional. So converse and inverse are logically equivalent to each other. Next we have logical implication. We will understand the definition for logical implication first. The conditionals P implication Q, where P and Q are related in such a way that the truth value of Q depends on the truth value of P or vice versa. Such conditionals are called hypothetical or implicative statements. So it says that for the given conditional P conditional Q, P and Q are related in such a way that the truth value of Q depends on the truth value of P, or it might be vice versa. So sometimes what happens, the truth values of P and Q are depending on each other. So if that is the case, then such conditionals are called hypothetical or implicative statements. Now, when a hypothetical statement P conditional Q is such that Q is true whenever P is true, we can conclude that P implies Q, and we write it symbolically P implies Q. This is the implies symbol for us. Right? We are familiar with this implies symbol, no? So this represents P implies Q. So hypothetical statement P conditional Q is such that Q is true whenever P is true. So whenever we have P to be true, in such cases Q is resulting to be true, then we say that P implies Q. P implies Q. Similarly, when a hypothetical statement P conditional Q is such that Q is not necessarily true when P is true. Q need not be true when P is true. Then we say that P does not imply Q, and symbolically it is written as P does not imply Q. So this symbol represents does not imply. Does not imply. So these are the definitions for logical implication. So if I have to say that the given expression is logically logically implied to the other one, to the other proposition, then it has to satisfy the condition that whenever P is true, Q must be true. If not, P is not implying to Q. So this is all about the theory part. So we learnt about NAND, NOR, followed by converse, inverse and contrapositive, and now logical implication. Now we will work out problems on these topics. Problems. First question. Express negation P or Q, P and Q, P implication Q using NAND only. We have to express negation P or Q, P and Q and P conditional Q using the NAND connective only. So let us do the solution for this. So first one, for any proposition P, we have P and P is logically equivalent to P itself. This is one of the law what we learned in the laws of logic, that is idempotent law. Due to idempotent law, we will be able to write down P and P is logically equivalent to P itself. Next, we will be now able to represent negation P. So negation P is logically equivalent to negation of P and P. So we just had P here. Now P is represented as P and P using idempotent law. So I have negation P means that can be written as negation of P and P. So negation of P and P is nothing but P NAND P from the definition of NAND. NAND is a combination of not and. So from the definition of NAND, we will be able to represent negation of P and P as P NAND P. NAND represents the up arrow, right? So we have represented the first part of the question, that is negation P with the logical corrective NAND only. That's the solution. Second one, we have to do it for P or Q. So P or Q. P or Q, using the law of double negation, we can represent it as negation of P or Q. Negation of P or Q. This I have used law of double negation. Law of double negation. Using that, we have represented P or Q as negation of P or Q. Correct? Now, we will use De Morgan's law for the big bracket. Negation of P or Q is nothing but the outside negation I am writing as it is. So we have negation P and negation Q. Negation P and negation Q. So here I have applied De Morgan's law. Using De Morgan's law, we obtain negation of P or Q is negation P and negation Q. So that we observe the next step. Before I do the next step, okay, let me show it to you. Here, negation P I assume as, say, capital P. Negation Q I assume as, say, capital Q. So that this is of the form negation of P and Q. Negation of P and Q. This is logically equivalent to P NAND Q using the NAND definition. Right? Negation P I assume as capital P. Negation Q I assumed as a capital Q. So that this expression is of the form negation of P and Q. So negation of P and Q from the definition of NAND, this is logically equivalent to P NAND Q. so that we can now express this expression in the form P NAND Q. So that will fetch me, in place of P I have negation P, small p, NAND negation Q. Negation P, NAND negation Q. We have to express with only the logical connective NAND. So now I can write down negation P. How can we write down negation P using the answer for 1 that we obtained? We obtained negation P is logically equivalent to P NAND P. So similarly, negation Q, I can write down that it is logically equivalent to Q NAND Q. So both these places I will be using again NAND connective. So this is logically equivalent to P NAND P, and there is a NAND again, Q NAND Q. So if we observe the resultant now, it is full of only the connective NAND. That is our requirement. Read the question once. We have to express each of these connectives using NAND only. Right? So we have expressed using only NAND. That's the answer for the second subpart of the problem. Now moving ahead to the third one, third subpart of the question. We have to express P and Q. So we consider P and Q. P and Q is again logically equivalent to negation of P and Q. So here again I have used the law of double negation. I'll just write the same thing. We have used the law of double negation and we have obtained this expression. Negation of P and Q gives us P and Q. P and Q. Next, again we will use De Morgan's law within the big bracket. Within the big bracket, we will use De Morgan's law and write this down as negation of negation P or negation Q. Negation P or negation Q using De Morgan's law. Using De Morgan's law, we have obtained this. Next, I will assume this entire expression within the big bracket, whatever I have, I will assume this entire expression say capital P. This entire expression I am assuming as say capital P. So this is now of the form negation P. Correct? So now it is of the form negation P. We observe from the first part that negation P is logically equivalent to P NAND P. In order to express in terms of NAND, so this can be written as P NAND P. P NAND P. So I'll be expressing the same thing in the form of P NAND P. Okay. So we have this is logically equivalent to P. What was that expression in the left hand part? P and Q is logically now equivalent to, we have to now express in the form P and P. P is nothing but the entire big bracket, what you can see in the previous step. So it is negation P or negation Q and the same thing. Negation P or negation Q. Right? So this is logically equivalent to writing down this now in the form negation P or negation Q is nothing but negation of P and Q. So we will represent that for the first one. Negation of P and Q. We have NAND in the middle. Again, this is negation of P and Q. Negation of P and Q. Now, how can I represent that negation of P and Q? We can represent it as P NAND Q. P NAND Q using the definition of NAND. This is nothing but P NAND Q. We already have a NAND in the middle. Write it down as it is. Again, we have P NAND Q. The entire expression now is full of connective, only the NAND. NAND connective is being only used. Correct? So P and Q is now logically equivalent to P NAND Q, NAND P NAND Q, fully expressed in terms of NAND only. Now the fourth part of the question. Fourth one is to express the conditional P conditional Q we have to express in terms of NAND only. So recall the definition for P conditional Q. P conditional Q is always logically equivalent to negation P or Q. Negation P or Q. And this is logically equivalent to negation of P and negation Q. So this is something like taking common kind of. So using De Morgan's law, so negation P or Q can be written as negation common outside, P as it is, or becomes and Q becomes negation Q. Using the De Morgan's law concept, we will be able to write down like this. So negation of P and negation Q we have obtained. So again using the NAND connective, this can be written as P NAND negation Q. Right? Definition of NAND is a combination of not and AND. So not and AND can be replaced by the NAND symbol. So P NAND negation Q. Now P NAND negation Q is logically equivalent to writing P NAND negation Q can be written as Q NAND Q. Using the first part of the problem, that is we learned it that we can write down negation P as P NAND P. So same manner we can write down negation Q as Q NAND Q. So again we observe the entire expression is with respect to NAND connective only. So that's the solution for the problem. So we expressed few things, few connectivities, whatever was given, we expressed everything in terms of NAND only. Now we'll see second problem. Second problem I would like to take up on converse, inverse and contrapositive concept. Okay. So question, if m divides n and n divides p, if m divides n and n divides p, then m divides p. Then m divides p. The question is to write the converse, inverse and contrapositive for the following. Write the converse, inverse and contrapositive for the given statement. Write the converse, inverse and contrapositive for the given statements. So first let us write down the given statements or the propositions in terms of P, Q and R. So I have one proposition as m divides n. The second proposition I can read it as n divides p. And thirdly we have m divides p. So we will respectively write them and represent as PQR. PQR. So let us assume P denotes m divides n and let Q be n divides P and let R be m divides P, so that the given statement reads in the form P and Q conditional R. So remember or recall the property for conditional. Conditional is nothing but if P then Q. So here we have and also in the middle. So it is nothing but m divides n is p, n divides p is q. So we have p and q. Then, if then, so conditional. M divides p is nothing but r. So p and q conditional r. P and Q conditional R is the given proposition for this. So for this we have to write down the converse, inverse and contrapositive. So let us write down one by one. So first one, converse. Converse. So converse is given by, how is the converse can be written of this? Recall the definition for converse of the given statement. Converse says that if you have the question in the form P conditional Q, then Q conditional P gives us the converse. Q conditional P gives us the converse. So we have to write it down, R conditional P and Q. R conditional P and Q. This is the converse of the given statement. So now we have to write it in words. Without fail, we have to write it in words also. So what does it say? If m divides p, then m divides n and n divides p. So how did we write it down in this? I'll just explain. R stands for m divides p. So I have conditional. Conditional is always read as if p then q. If p then q. So that is why R stands for m divides p. So if m divides p, then conditional says if then. So that is why if then is being used. P and q. P and q you have to represent. So m divides n and n divides p. M divides n and n divides p represents p and q. So that is how we have written the converse of the given statement. Now we will write on the inverse. Inverse of any conditional is given by. Recall how is the inverse of any conditional given by. Suppose the given conditional is P conditional Q, then the inverse is given by negation P conditional negation Q. Negation P conditional negation Q. So this is my given expression, no? Given statement is P and Q conditional R. So for this I have to write on the inverse. The inverse of this is negation of P and Q conditional negation R. I am assuming P and Q as say capital P, R as say capital Q, then P conditional Q is of that form. So inverse of the conditional is negation P conditional negation Q. So that is why negation of P and Q conditional negation R has been written. Right? So now we write down the same thing in the form of words. Before writing down in the form of words, we can use De Morgan's law here and split the terms. So using De Morgan law, this is one and the same as writing negation P or negation Q conditional negation R. So we can also read it as if negation P or negation Q, then negation R. We can read it in that manner also. We will put the same thing in words now. Negation P means if m does not divide n, or there is a or symbol in the middle. There is a or symbol. Negation Q. Negation Q means n does not divides p. N does not divides P, then if then, conditional says if then negation R. Negation R means M does not divide P. M does not divides P. M does not divides P. So this is how we can write down in the form of the statement, the inverse of the given conditional. The third one, we have to find out the contrapositive. So what is contrapositive? Recall the definition. P conditional Q. Given proposition is of the form P conditional Q means the contrapositive of the same is negation Q conditional negation P. Negation Q conditional negation P gives us the contrapositive. Contrapositive we will write down now. Contrapositive. So contrapositive we have to write down. As I mentioned, P conditional Q is the given conditional means contrapositive is given by negation Q conditional negation P. So negation Q means negation R. Negation R conditional negation P. So negation of P and Q. Negation of P and Q. Again using De Morgan's for the second expression there, I can write it down as negation P or negation Q. Negation P or negation Q. We'll put the same thing in the form of words now. Negation R means if then, conditional represents if then. So that is why we have to write down if M does not divides P, M does not divides P, M does not divides P, then negation P. Negation P means M does not divide N. Similarly, negation Q means N does not divide P. So then M does not divide N, M does not divides N, and N does not divides P. So that is how we write down the converse, inverse and contrapositive of the given conditional. Now we will see another problem. Third problem. Write down the contrapositive of P conditional, open a bracket, Q conditional R with first condition, only one occurrence of the connective, only one occurrence of the connective. The connective given is conditional or implication. Second one, no occurrence of the connective. No occurrence of the connective, that is implication. So given question is P conditional, Q conditional R. You have to represent this. First you have to write on the contrapositive of this. And for the contrapositive, you have to represent the answer with only one occurrence of the conditional and no occurrence of the conditional. Right? That is our question. So let us see how to do the problem. Let us understand and do how to do the problem. We will see. The contrapositive we will write down first. Okay. So what is the contrapositive of P conditional Q? There's a bracket for this, no? The bracket term we assume as say big letter Q. And P we will assume as say big letter P. So it is of the form P conditional Q for us. P conditional Q. And the contrapositive of P conditional Q is negation Q conditional negation P. Negation Q conditional negation P. We'll write on the same thing first. The contrapositive of P conditional Q conditional R is negation of Q conditional R conditional negation P. We assume P as P and Q conditional R as set Q. So P conditional Q is the given statement. So for P conditional Q, the contrapositive is negation Q conditional negation P. Right? Now we consider this expression and prove the requirement 1 and 2, that is with only one occurrence of the conditional and no occurrence of the conditional symbol. Okay, so consider negation of Q conditional R conditional negation P. This is logically equivalent to writing it is of the form P conditional Q for S. Let us remove this conditional now first. Okay, so what I mean to say is this is of the form P conditional Q. P conditional Q form I am assuming. Okay, so this entire expression, that is negation Q conditional R, I am assuming as P, and negation P I am assuming as Q. So it is of the form P conditional Q. So what is P conditional Q? P conditional Q, we are familiar that this is logically equivalent to negation P or Q. Negation P or Q. Now we will use this and rewrite the given expression negation P or Q form. Okay, so negation of, this will be logically equivalent to negation of negation P. P means Q conditional R, negation Q conditional R or negation P. We have removed this outside conditional symbol. There was a outside conditional symbol. No, we have removed this using the formula P conditional Q is logically equivalent to negation P or Q. So negation P or Q we have written. This bracket should have been closed at the before only. Okay, so I will just rewrite it once again for you. So this should have been closed before. Okay, no? So negation of negation Q conditional R or negation P. This becomes negation P or negation P or Q form. Okay. Now negation of negation is nothing but law of double negation. So the given expression will be now logically equivalent to Q conditional R or negation P. Using the law of double negation, both the negations are removed. So we just remain with Q conditional R or negation P. Right? So I'll just call this as expression number 1 or the answer for the first one. No, this will be the answer for the first one because first one says only one occurrence of the connective. So we have only one occurrence of this connective and we have the answer for it. Okay. Now we have to remove this occurrence also for the second part of the problem. No occurrence of the connective, the arrow, right arrow. So Q conditional R again can be written as negation Q or R. Negation Q or R. Outside I already have or negation P. I will retain it as it is and this gives us a solution for the second one. We have removed both the implication symbols and we have obtained this answer. So expressions 1 and 2 gives the required answer. So therefore expressions 1 and 2 gives us the required answers. Correct? So this is how we work out problem for a contrapositive by removing the conditional symbol. So next I would like to work problems on logical implication for you. Logical implication, we will just recall the definition for logical implication. So P conditional Q, the conditional is in such a way that whenever P is true, Q must be true. So we say that P implies Q. This is happening only whenever P is true, Q must be true. Then we say P logically implies Q. That's the definition for logical implication. So we will work out the next problem based on logical implication. Fourth one. Prove that P conditional Q and negation Q implies negation P. We have to prove that P conditional Q P conditional Q and negation Q implies negation P. So can I say that this is actually of the form, say this expression is of the form capital P, the bracket term. I have to prove P implies Q. So I have to prove that this is P for me, this entire expression. So P implies Q I have to prove. If I have to prove P implies Q, it means that I have to assume whenever P is true, I should obtain Q should be true. So using the truth table, we will be able to write down this. So we will write the truth table for the same now. Solution. We have only two propositions P and Q. So we write down P and Q and frame the truth table for us. PQ. We will be in requirement of P conditional Q. Next we have negation Q. Then we will be taking AND between these two. So P conditional Q and negation Q we will be considering. P conditional Q and negation Q we will be considering. I'll just put a bracket here for convenient. Then lastly we have negation P. We'll form a table first and write down the truth values of P and Q. What are the truth values that P and Q takes? It takes 0, 0, and then 0, 1, 1, 0, 1, 1. We'll represent them one by one. So it takes the truth values 0, 0, 0, 1, 1, 0, 1, 1. 1, 0 and then 1, 1. What is P conditional Q first? P conditional Q is nothing but P conditional Q is 0 or takes the truth value 0 only when P is taking 1 and Q is taking 0. Only when it is 1, 0, the truth value is 0. Rest all cases it is 1 only. 1, 0 only gives us 0 for the conditional. Rest all cases it is 1. Now negation Q. When it is 0, negation Q is 1. When Q is 1, negation Q is 0. Now we will take AND between these two, P conditional Q and negation Q. AND definition we will recall, only when both P and Q are 1, the resultant is 1, rest all cases it is 0. So only in the first row we have 1 as the truth value, rest all it is 0. That is the definition for AND. Now we take negation P. Negation P will give us 1, 1, 0 0, 1 1 0 0, negation P. Now what is to be observed? We have prepared the truth table, that's fine. Now we have to show that P implies Q. P means this P conditional Q and negation Q. I have to show this implies Q. So how is that to show is, see, whenever P is true, Q must be true. That is the definition for logical implication. So whenever P is true, here only I have P to be true. So whenever P is true, we observe that Q is true. Q is true. So these are helping me to show that the expression in the left hand part implies right hand. That is, P implies Q is possible, is true, is true. So we have 1 here, P conditional Q and negation Q is 1. When this is 1, negation P should be 1. We are not seeing the other way. Whenever negation P is 1, we do not expect this conditional and negation Q to be 1. So whenever P conditional Q and negation Q is 1, negation P must be 1. That is the definition for logical implication. So from the truth table, we observe that P conditional Q and negation Q is true, then negation P is true. So therefore, we can conclude, what can we conclude? P conditional Q and negation Q implies negation P. That's the solution for the first one. We'll see one last problem on logical implication. Fifth question. P or Q or R, P or Q or R and negation Q. There is a bracket for P or Q or R and negation Q implies P or R. So we have to prove this. That P implies Q, where P is nothing but P or Q or R and negation P, and we have to prove this implies P or R. So again we will frame the truth table and we will obtain the resultant. So we will just write down the solution. So we will frame the solution now by writing P first, then followed by Q, then R. There are three propositions, P, Q, R, correct? So we have to write down the truth values of P, Q, R, then frame the table with these P, Q, R. So we have Q or R required, Q or R. Then we take P or Q or R. Then we take negation Q. Okay, we will frame the table for this first and just put lines. P, then followed by Q, then we have R, then Q or R, then P or Q or R, then negation Q. The continuation I'll put it in the next page. It is not possible for me here. So if you have enough of place, it's always well and good. So truth values of P, Q, R, we will write down one by one. So truth values will be starting from 0, 0, 0. So starting from 0, 0, 0, then we have 0, 0, 1, 0, 1, 0, then we have 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and lastly 1, 1, 1. So we will write down first Q or R. Q or R takes the truth value 0 only when both Q and R are 0. Only when both Q and R are 0, rest all places it takes truth value 1. Next we have P or Q or R. Again or between these two, first column and the fourth column you have to look into. P or Q or R you have to look. So only when both have truth value 0, the resultant is 0. First and the fourth column I am looking into. So rest all are ones. Next we take negation Q. Negation Q gives us 1, 1, 0, 0. Again 1, 1, 0, 0. Right? Now what else is left over for us to write down? So I have to write down this left hand part of it, that is P or Q or R and negation Q. So and between these two I have to represent, and I have to write down P or R. Right? So we will do that in the next page. If you have the place, sufficient place, please do there only. It will be convenient for you to look into the values of P, Q, R and do it. Okay. So next I will be doing it. So I have to take the left hand part of it, that is P or Q or R, P or Q or R, and negation Q I have to consider. And this has to imply P or R for us. This has to imply P or R. So I'll just again put this in the form of a table. So we will look into the previous page table and do this. So we have and between the last two columns what we did. P or Q or R and negation Q. P or Q or R and negation Q. So and means when both the truth values are 1, then only the resultant is 1. That is second row I can put it as 1, and then I can put for the fifth and the sixth row. Correct? Rest all are zeros for us. So I will just fill the same thing. Second, fifth and the sixth row. Second, fifth, sixth are ones. Rest all are zeros. I'll just repeat that once again. P or Q or R and negation Q have to do. So and between these two columns. And definition says that only when truth values of both these columns are 1, the resultant is 1. So second row 1 1 I have, so resultant is 1. Fifth row I have 1 1. Sixth row I have 1 1. So resultant is 1 only in the second, fifth and the sixth row. All other truth values are zeros. All other truth values are zeros. That's what I have written here. Next we have to consider P or R, or between first and the third column, P or R. So P or R we will do P or R. Or means if there is only any one of them having the truth value 1 is sufficient to write down the resultant as 1. If both are zeros, then the answer is 0. So P or R, first row both are 0, third row both the truth values are 0. First row and the third row P or R gives us 0, rest all are ones. Rest all are ones. First row is 0, third row is 0, rest all are ones. Correct? So we have filled this now. Now what is to be verified? What we are supposed to verify, I will just show it to you that. So we have to prove that this implies P or R. So implies means whenever P is Q, whenever P is true, Q should be true. So we observe whenever this is true 1, so the P or R is true. So whenever the left hand part is true, that is P or Q or R and negation Q is 1, this should be 1. So these are the observations that we have done here. So whenever P or Q or R and negation Q is true, this is true in 3 cases. Whenever this is true, P or R must be true. P or R must be true. Other than this, this P or R might have another some other truth values. It does not matter. Only when this P, this entire expression, if I assume as say capital P, so whenever capital P is true, I should have Q should be true. Q should be true. So that is how we get this. So observing the same thing, we can conclude that P or Q or R and negation Q implies P or R. Implies P or R. Right. So that is all about problems based on logical implication. So in today's session, we saw problems on converse, inverse, contrapositive, logical implication, and as well as we saw problems on NAND and NOR gates, NOR connectives. Thank you for watching.